Okay, we are recording. All right, today we're going to be looking at uh, images formed by curved mirrors. And for what we're doing, we're actually using spherical mirrors. So, however, we're going to stay close to what they refer to. I can't remember the exact term they use, but we're going to define a line on these spherical mirrors. And the spherical mirror will have some center of curvature here where this will be the radius of the spherical mirror. And they draw something that's sort of like an axis of the mirror. And what we'll do is we'll actually consider only mirrors where we're going to consider a part that's within a fairly short distance of this axis in either part of the mirror. So it'll be a small section of a spherical mirror. And then when we consider stuff like objects for which we might form images, we'll only consider things that are not very far away from that axis. And in the very first part of section 34.2, I think it is, they derive a couple of equations for this, and you might go through those. They depend on some small angle approximations, and it's not too hard to follow, but try to work your way through that so these don't just seem like magic. But if you've got a distance here, this is going to be the distance S from the mirror to the object. So there's our object. And let's see. I think they start off with something that's actually farther away than what I've got here. But then there would be an image that forms somewhere. And maybe we're not going to worry right now about whether the image is right side up or upside down. That'll come out in the math. But if that's the image, then S prime is the distance from the image to the mirror. And so that's what we'll have. And they developed this equation. And it's this. It's that 1 over S plus 1 over S prime. And if you go through the development, you'll see why these things show up as reciprocals, is equal to 2 over R. And so that's an equation that we can use for figuring out if you're given the object distance, the S, you'll be able to figure out what S prime is, or if you're given both of them, you can figure out what the radius of curvature is. And then they have you consider, well, what if the object is really far away? Okay, well, yesterday I introduced the idea of the focal length, and the focal length is or the focal point. That's the point where incoming parallel light rays will focus. Okay, well, if an object is really far away, the light rays that come from that object will be parallel, and they'll come to a focus at that focal point. And the focal length was the distance from the mirror to where that image or where incoming light rays will focus. And so if for a very distant object, one over S is going to be about equal to 0. And so what you'll have is that 1 over S prime is just going to equal 2 over R, but that's going to equal, S prime is going to equal the focal length. So you'd have 1 over F. And what this tells us, if a simple fraction equals another simple fraction, you can just flip them both, and you get that the focal length is actually half of the radius of curvature. Let's see, years ago, I started grinding a telescope mirror, and for some reason, I keep having home projects that percolate closer to the top of my list of things to do than that telescope mirror, so I haven't quite finished it. I need to polish it is what I do and then parabolize it. But when you start grinding a telescope mirror, the first thing you do, you start using something called a tool, which you set on top of the mirror blank, and you rub that tool against the mirror blank initially to make a kind of a concave thing. And a concave mirror, concave surface, this would be the part that's going to become the mirror. That's concave. And for a mirror, you'd pretend that light never gets back here. And so this is actually part of it. This is the surface that'll become the mirror. Anyway, concave, you can remember that if you think if it was really concave, it'd be kind of like a cave. So that's how you can remember that. I don't know how you're supposed to remember convex. You just remember that concave part. Convex is the opposite. So convex would be a mirror that looks like this. And no light gets behind the surface. So here's convex. Anyway, you start grinding this convex surface, and I wanted to have now this is going to be inches, so bear with me, but I wanted to have one with a focal length of about 48 inches. And the reason I wanted it that long was actually it's a common focal length for a small 8-inch diameter mirror telescope. But if that's the focal length, you can have your telescope length be less than 4 feet or 4 feet or less. And that's a size that would fit easily in the back of the van that I had at that time, going sideways. And so it's just a convenient size telescope. But when I started grinding it, I wanted that's a 4-foot focal length. That makes, and the radius of curvature is twice the focal length. That would make an 8-foot radius of curvature. Well, the way I could draw that radius of curvature was that I pinned something down here and had a piece of string here with a little loop at the end, and this was 8 feet. And I used that to draw a circle on a piece of cardboard. And then I just cut out that circle and the piece of cardboard there, and this was that edge. And I kept grinding the mirror, and every once in a while I would bring this little chunk of cardboard that had that 8-foot radius of curvature on it and set it on there. And when I started zeroing in on the 8-foot radius of curvature, then I started switching to a finer grit, or maybe one that wasn't quite so coarse. When you start off grinding the mirror with this really coarse grit, it almost sets your teeth on edge listening to the sound that it makes grinding this glass away. But anyway, that's something that you do. So here's a couple of equations that, whoops, we'll have this one, but we'll also extend that and just go to 1 over F. And so that's part of what we're going to use today. Something else that comes out of this is the magnification of the object. If you compare the image height to the object height, you'll get a magnification that's going to show up on this thing. And it ends up being, and they developed this formula in the textbook as well, minus S prime over S. And so, well, that's the image distance divided by the object distance. Also, somewhere here, I just printed it. Thought I did. Oh, it's on the back of here. Um, this is the thing that has sign conventions for mirrors. And this is, I'm going to give you this handout for the test, but I've made it up. I put it up on today's, so you can print this off for yourself if you want. We're going to be doing mirrors today, refracting surfaces tomorrow, or actually Monday, and then lenses next week. And so we'll spend a few days on this stuff. But sign conventions for mirrors. S is positive if the object is in front of the mirror. For now, those are the only kind of objects we're going to consider. Later, we'll consider some virtual objects. S prime is positive if the image is in front of the mirror, in which case that'll be a real image. And we do the math to figure out what S prime is. And then S prime is negative if the image is in back of the mirror. That'll be a virtual image. And then for mirrors, the focal length and the radius of curvature are positive if the center of curvature is in front of the mirror. That's a concave mirror, like this one. And for a convex mirror, F and R are both negative. It'll be in back of the mirror. Back is the side the light never gets to. So for a convex mirror, let's see, where's my little circle drawer thing? Oh, well, around here somewhere. Anyway, convex mirror, that's one where the light is on this side. This is the real side, or the front is what we call it in this case. And here's a convex mirror, so the mirrored surface is on this side, and on this side, light never gets to it. So that's where I draw the dashed lines there. But the center of curvature is going to be over here. And then that center of curvature is twice the focal length. Here's the radius of curvature. And the focal length would be in here, half that distance. So that's a convex mirror, one of those ones with the negative center of curvature. So anyway, let's go ahead and solve some example problems today and see how these things work out. And this is a problem that I accidentally printed twice in the handout, or put twice in the handout for today's material. So the second time you see it, don't bother to do all the problems or all the parts of it again. But we have a concave spherical mirror that has a radius of curvature of 20 centimeters. Okay, so make a note of that. It's also concave, which means the radius of curvature is going to be positive. If I look at my thing here, F and R are positive if the center of curvature is in front of the mirror, and it says it's a concave mirror, so that's one that has that. Okay, so anyway, R is going to equal 20.0 centimeters, which is twice the focal length. So the focal length is going to equal half the radius of curvature, or 10.0 centimeters. So I know those things so far. Oh, and I'm supposed to find the location of the image for object distances of 40 centimeters, 20 centimeters, and 10 centimeters. Well, sounds like I'm going to have to use this equation 3 times. 1 over S plus 1 over S prime equals 1 over F, or I could say it's equal to 2 over R. But this is kind of a pain in the neck to have to solve this thing 3 times. However, I can simplify it. If I solve this algebraically once for S prime, I can use that equation again and again. And I'll show you this. I don't give you this formula on the test, but you should be able to solve it for it yourself fairly quickly. 1 over S prime is going to equal 1 over F minus 1 over S. Well, I don't want 1 over S prime. I want S prime. So I'm going to work on this fraction, or this expression over here, and turn it into a simple fraction. Because if I've got simple fraction equaling simple fraction, I can just flip them both. And what I'll do is over here, get a common denominator. Looks to me like it'll be F times S if I multiply the top and the bottom of this by S and the top and the bottom of this by F, I'll have a common denominator. And what I'll get is 1 times S is just S. I'll get S minus F over F times S. And that's equal to 1 over S prime. Simple fraction, flip them both, and I get S prime is going to equal F times S over S minus F. Okay, well, that's kind of nice. Now I can just plug into this thing and see what I get. So for A, now remember, F is 10 centimeters, but for A, I have S is equal to 40.0 centimeters. And again, F is 10 centimeters. So S prime will equal F, my 10 centimeters, times S, my 40 centimeters, divided by, oh, let's see, S minus F. So 40.0 centimeters minus 10.0 centimeters. That's 30 on the bottom. 10 times 40 is 400. 400 divided by 30, you can just about do it in your head. 30 will go into 390. How many times? 13 times. Okay, this ends up being 13.3 centimeters when you solve for it. Now, is that going to be a real or virtual image? Well, go to my sign convention. If S prime is positive, the image is in front of the mirror and it's going to be real. So that's a real image. Is it going to be upright or inverted? Well, I can figure that out if I look at the magnification of it. If the magnification is positive, it's upright, but here's the expression for magnification. It's minus S prime over S, which is minus 13.3 centimeters, 13.3, divided by 40, which is actually minus 1/3. And the negative sign tells me that it's upside down, so it's inverted. And it's 1/3 the size of the original. So if the original was, say, a candle that was 10 centimeters tall, the image is going to be an upside down candle that's only 3.3 centimeters tall, 1/3 of 10. And you can make a sketch of this fairly easily. This will just look like, here's my, what's going on here. I had the radius of curvature was 20 centimeters. My object is twice that far away. So here's my little, I'll just draw an arrow because that's easy to do. And I get, this is 10 centimeters. Nope, that's the radius of curvature. It's 20 centimeters. The focal length is halfway in there. But anyway, there's my object. So, and I figured out that the image was 13.3 centimeters here. Here's that. It's going to be out about here. And the image is 1/3 the size of the original. That's approximately 1/3. And it's upside down. So that's where the thing happens to be. Well, that wasn't too bad. A few steps there. Let's do another one. For part B, we've got S is equal to 20 centimeters. So S equals 20.0 centimeters. S prime is going to equal the focal length times S, 10 centimeters times 20 centimeters. Divided by S minus the focal length, which is 20, oops, these are each 0.0, 0.0, 20.0 centimeters minus 10.0 centimeters. So that'll be a 10 on the bottom. And let's see, it'll divide out with that 10. I get 20.0 centimeters for S prime. Okay, so the object and the image are at the same spot. And I can figure out and it's positive, so it's real. I know that. And magnification is minus S prime over S. Well, that's minus 20.0 centimeters over 20.0 centimeters. That looks like -1 to me. And so it's going to be upside down. And what else can I say about this? I don't know. That's just what it happens to be. So let's go ahead and make a sketch of this one. Same geometry, except I'm moving the object into here. So here's the center of curvature. Here's the object. And the image in this case, that's the image, is at the same spot, but it's upside down. Okay, well, that's kind of interesting. We might be able to experiment and do something like this in the classroom with the big telescope mirror. So anyway, that's that particular case. Now, the last part on here is I'm putting the object at 10 centimeters. That's the focal point. Okay, I'm just going to kind of continue down here for part C. So S is going to equal 10.0 centimeters. And in that case, S prime is going to equal its F times S. So it's going to be 10 centimeters times 10 centimeters on top. And on the bottom, I'll have S minus F. Oh, well, that's going to be 10 centimeters minus 10 centimeters. I think that's 0. And if you divide by 0, it's undefined. Okay, in this case, there's no calculating the magnification because you don't have an image. It blows up. That's what happens when you put an object at the focal point, because light rays coming in from on parallel lines bouncing off the mirror converge at the focal point. But if you have an object at the focal point, the light rays that come off of it bounce off the mirror and travel in straight lines. By the way, this is something that if you've ever seen a spotlight, let's see, I don't think they do this in Moses Lake, but it used to be if there was some big event going on at some place if you're in a city, like a car dealer, or maybe Best Buy would be having a big sale, or something's going on at a movie theater, some big movie opening, they would have a spotlight. And a spotlight is this thing with a concave mirror on it. It's not that thick. But anyway, there's the mirror. And up here at the focal point, so this would be the distance to the focal point, they have a bright light out there. Okay, well, any light that comes off of that bright light bounces off the mirror parallel to the optical axis, we call it. And so doesn't matter where it hits the mirror, it all comes off parallel. And so you get this big parallel beam of light. And that's how you can make a spotlight anyway. And that's what we've got in this case. Now, something they don't do on this problem is put something inside the focal point. So I'm going to augment this problem and do this. I'm going to let S equal 5.0 centimeters and see what I get for where the image is going to form. So S prime, remember my formula, F times S over S minus F. It's going to be 5.0 centimeters times 10 centimeters. Whoops, I'm reversed the order, but I think multiplication is commutative, so that part doesn't matter. And then on the bottom, I'll have the S minus F. That's going to be 5.0 centimeters minus 10.0 centimeters. And what do I get in that case? Let's see, that's going to be -5 on the bottom. It'll divide with that and give me -1. It'll be minus 10.0 centimeters. Okay, well, what does that mean? Well, first of all, it's negative. That tells me it's a virtual image, not a real image. And I can draw a picture to kind of figure out where this is. If this is negative, it's in back of the mirror. Excuse me. S prime is negative if the image is in back of the mirror. That's a virtual image. So here's what happened. I had this object, let's see, draw my mirror here. Okay, there's my concave mirror. It's got a focal length or focal point of 10 centimeters, but I just put this object here half that distance from the mirror. And what I get for this is a negative distance to figure out if it's real or inverted or right side up. I take the magnification, which even for this kind of image, it's always minus S prime over S, which is going to be negative of negative 10.0 centimeters, and S was 5.0 centimeters. Well, negative times negative is positive. The magnification is going to be +2. So let's see, this is twice as far away as the object was. Here's going to be S, is that distance. S prime is going to be twice that distance, so it's going to appear behind here, but it's going to be twice as big. So here's the image. It's upright and it'll be twice as big as the original. So all that stuff I can tell by looking at these equations. Okay, well, that was good. Let's see. Oh, that was yesterday's problem. Now, here's one. We've got an object's image in a 27 centimeter focal length concave mirror is upright. Okay, it's concave, so it's a positive focal length. So I can do this. F is equal to plus 27 centimeters, upright and magnified by a factor of 3. Okay, that tells me the image or the magnification is going to be +3, which is minus S prime over S. Okay, oops. Yeah, it's equal to that, minus S prime over S. Well, what does that tell me? I can solve or multiply out from underneath by S, and I'd get minus S prime is equal to 3S. And so that's something I can do. I haven't had to use a calculator yet on these problems, I don't think. I'll hang on to that stuff. Well, my formula is 1 over S plus 1 over S prime is equal to 1 over F. I happen to know F. I don't know what S and S prime are, but I do know that minus S prime is equal to 3S, or I can say that S prime equals minus 3S. How's that sound? So I'll just do that. 1 over S plus 1 over minus 3S, which becomes 1 over S minus 1 over 3S. is equal to 1 over f. And this, if I multiply top and bottom of this one by 3, I will get 3 minus 1 over 3s is equal to 1 over f. Where's the object? I want to know what s is. Well, that's 2 on top. So 2 over 3s is equal to 1 over f. Whoops, 1 over f. Simple fraction equals simple fractions. Flip them both. So 3s over 2 equals f over 1, but that's just f. So s is equal to multiply both sides by 2/3, and it's equal to 2/3 f. And 2/3 of f is 18 centimeters. So that's where it happens to be. And with that, where s prime is going to be, it's going to be minus 3s. So negative 3 times this will equal minus 54 centimeters. But here's something that's important. Anytime you have an object or a concave mirror that's inside the focal length, you end up with an image behind the mirror. And it'll also be upright. The image will, and it'll be magnified. In this case, it's 3 times. Oh, did we figure out the magnification? That'll be minus 3s over s. It'll be a magnification of 3. Whoops, that's a minus 3s up there. Yeah, magnification of 3. Yeah, but anytime, if this is the focal point there, so the distance to the mirror is the focal length, maybe they use an uppercase F for the focal point. I'm not sure. But anyway, F is the distance from that spot to the mirror. But if you put the object inside of that, you end up with the image being behind the mirror. And it's a virtual image in that case because light is not diverging from a point behind the mirror. It just looks like it is. And that's what a virtual image is. Okay. Here's yet another one. These problems are usually pretty simple, but you need to work a bunch of them to develop some facility in dealing with this. But at what 2 distances could you place an object from a 45 centimeter focal length concave mirror? All right, it's concave, so it's got a positive focal length. And in this case, F is 45 centimeters, 2 sig figs on that. We want an image that is 1.5 times the object size. That means the magnification is either going to be plus 1.5 or the magnification is going to be minus 1.5. Either way, the image will be 1.5 times the object size. Well, if it's in either case, the magnification is, let's see, minus s prime over s every time. So let's see, with the negative magnification like that, I'd have negative magnification. If it's minus 1.5, that tells me that s prime will equal 1.5s. Minus on both sides. I can multiply both sides by minus 1 and get s prime over s is that. And I'd get that. Well, with a focal length of 45 centimeters, where is, I guess I could also say, oh yeah, I want to know where I can place the object. So 1.5 is 3/2. That tells me that s equals 2/3 s prime. Actually, this will work because I can say 1 over s plus 1 over s prime equals 1 over f. and I know that. I want to solve for S. Let's see. I'm going to do the same trick I did earlier when I was solving for S prime. No, let's just plug it into here. Okay. 1 over S plus 1 over 1.5 S is going to equal 1 over F. I multiply top and bottom of this by 1.5. 1.5. I bet on here I'll have 1.5 plus 1, which is 2.5 over 1.5 S is going to equal 1 over F. Let's see. 1 over F, excuse me. Flip both sides. I'll get 1.5 S over 2.5. I think this is 3/5 is equal to F. So if I multiply both by 5/3, I'll get S in this case is 5/3 F, which is 5 times 45 centimeters over 3, which is 45 divided by 3 is 15. 5 times 15 is 75 centimeters. So if I put the object at 75 centimeters away from the mirror, it could work. Let's check it to make sure. Okay. I'll use my solving for S prime equation, which I had a ways back. Here it is. S prime equals Fs over S minus F. So which in this case is going to be 45 centimeters times 75 centimeters, which is over S minus F, 75 minus 45, minus 45 centimeters. So S prime is equal to, that looks to me like 30 centimeters. We'll see if this works. Oh, rats. I'm going to have to use a calculator. I'm not doing that in my head. I could sort of do it, but I get it at 112.5. We've only got 2 sig figs, but okay, I'm going to get too many significant figures on here, okay? But if I do that, that the magnification in this case is minus 112.5 centimeters over 75 centimeters, which is actually minus 1.5. So that's where I get that negative one at. Okay, well, what if we have a positive magnification? Okay, in that case, I guess, oh good, a blank page. If I have M equals plus 1.5 equals minus S prime over S, that means that 1.5 times S will equal minus S prime, or it's the object distance I'm going to want. So I'm going to solve S prime is equal to minus 1.5 S. Okay, now, for the problems we're doing here, we cannot have if you've only got one light surface like this concave mirror, we can't have a negative value of S. Don't worry, those will be coming, but not yet, not today. So I'll just use that there. And I can say 1 over S plus 1 over S prime is going to equal 1 over F. I've got the same focal length as before. Remember, F equals 45 centimeters. Replace S prime with minus 1.5 S. And so 1 over S minus 1 over 1.5 S is going to equal 1 over F. And multiply top and bottom of this one by 1.5. 1.5 over 1.5 S minus 1 over 1.5 S is equal to 1.5 minus 1 is 0.5 over 1.5 S is equal to 1 over F. Flip both, and I get 1.5 S over 0.5 is equal to 1 over F. This looks like 3. So, whoops, is equal to F because I flipped it. Anyway, 3S is equal to F, or S is equal to 1/3 the focal length, 1/3 F, which is 15 centimeters. So we've got the object inside the focal length of the mirror again. And when we do that, let's see, our S prime is going to be negative compared to that 1.5 times this. So the S prime is going to be 22.5 centimeters. That's 1.5 times 15. 22.5 centimeters behind the mirror. And in that case, we get positive magnification. Okay, we get a virtual image and positive magnification. Oof. Okay. Let's do one that's a little more fun. This is the distance to the moon at perigee is 363,000 kilometers. Perigee is the part of the moon's orbit where it's closest to the Earth. Okay, and at that time it's 363,000 kilometers away. I'm going to draw a little picture here. If we've got a telescope that's looking at the moon here in the sky, so there's the moon, and this thing is subtending a pretty small angle in the sky. Okay, so this thing here is 0.55 degrees. And at some point, I'm going to want to know the diameter of the moon. Okay, so I think I'll just figure it out. Oh, this distance here to the moon is 363,000 kilometers. I'm going to convert that to meters pretty quickly just by adding 3 more zeros. But that's how far away it is. And if I convert this angle to radians, actually I'll multiply it by pi radians over 180 degrees. I'll be able to figure out what the diameter of the moon is from this. Remember where that problem was. I solved this earlier. Okay, there we go. All right. Anyway, this is 9.6 times 10 to the minus third radians. Okay. Now, something I can say is that D, I can treat it like an arc length. When it's an angle this tiny, even though it's a line connecting 2 points, the difference between, I think you call that a chord, the chord and the arc length is not significant when you're dealing with an angle this small. And so D over 363,000 kilometers is going to equal that many radians. Arc length divided by radius equals the radian angle measure. So that'll be 9.6 times 10 to the minus third radians. And this is just kind of preliminary, but they want to know how large the image of the moon will be. Well, if I figure out the magnification, then I can take the diameter of the moon and multiply it by that magnification and figure out how large the image is. That's my reason here. Okay, so the diameter of the moon anyway, and you could look it up, but this is more fun, is 363,000 kilometers times 10 to the third meters per kilometer times that 9.6 times 10 to the minus third radians. And turns out the diameter of the moon is about 3.5 times 10 to the sixth meters. Okay, the diameter of the Earth, the radius of the Earth is about 6.4 times 10 to the sixth meters. So its diameter is about 12.8. And this is approximately a fourth of that, which is about how the moon is compared to the Earth. All right, well, let's go ahead and use our equation here to figure out where the image forms. And I've got 1 over s plus 1 over s prime is equal to 1 over f. Well, this thing has a, let's see, 3.6 meters diameter, but a focal length of 8.5 meters. So that's the number that's going to go down here. But this is 3.63 times 10 to the 8th meters. That's going to go on the bottom of a fraction. That makes 1 over s about 0. And when you're using a telescope and looking at things that are far away, the image ends up forming at the focal point. So we'll have left a simple fraction equals a simple fraction. Flip them both and you get s prime is equal to f. The image forms at the focal length, or the focal length away from the mirror. Well, that's not too bad. Well, what's the magnification in this case? It'll be minus s prime over s. It's a real focal length or a positive focal length. So s, yeah, that's what it is. Anyway, s prime is equal to the focal length. So minus 8.5 meters on top. And s was, oh, I converted this. It's 3.63 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 over 63 times 10 to the 8th meters. So it's going to be a pretty small magnification. It ends up being, you plug in the numbers on that, minus 9.9 times 10 to the minus 9th. Okay, that's like 10 billionths of the size. And so, not very much. Well, if I take this, oh, also the minus sign tells me that it's going to be upside down. When you just have a simple concave mirror like that, looking at something, the image that the concave mirror forms is upside down. But that's okay. You don't care if it's upside down or right side up. If you're looking at the moon, you just kind of enjoy the view. Okay, well, the image height is going to be minus 9.9 times 10 to the minus 9th times the diameter of the moon. So times 3.5 times 10, that's 0.5, times 10 to the 6th meters. The image height ends up being 3.47 times 10 to the minus 2 meters. That's 3.47 centimeters. Well, what good was that telescope? You get an image that's, let's see, that's only about that big. Well, here's the neat thing. It's only 8.5 meters away from the mirror, floating, formed out there in space. what if, well, here's what you do with a telescope. Well, actually, this is a this is a professional telescope, 3.6 meters in diameter. That's more than 10 feet. But anyway, if it was a regular, just a Newtonian reflector, and it was used by what they're going to have at the focal point or near it is a camera, not a but the not an eyepiece. But if you had this, you'd be getting this image forming like that far away from the mirror. Well, what you do is before the image forms, you put in a diagonal mirror and bounce that image over here. And then you have an eyepiece here. So the image is like right there. And you put an eyepiece on there that's like a powerful magnifying glass. And you can look at that image that's right here. And you can look at it at your heart's content. And it's something that's 3.47 centimeters big. And you can use a good eyepiece actually magnifies it by quite a bit. And so you're magnifying a thing that's that big. And it'd be like looking at a moon that's floating right there in front of your magnifier. So that's how this thing works. So it seems crazy with that tiny a magnification, but end up with an object that's here inside your telescope or an image that's inside your telescope, and you can magnify it to your heart's content. Okay, well, oh, that's that same one we did earlier. So that was the one that's duplicated in there. Okay, a concave mirror with a radius of curvature of 1.00 meters is illuminated by a candle that is on the symmetry axis. That's something that they talk about on these things. 3.00 meters from the mirror. So let's go ahead and do a sketch here. Radius of curvature, all that. That be our 1 meter radius of curvature. And this thing's going to be 3 meters from the mirror. So 3 times that far away. 1, 2, 3. So there's where our candle happens to be. And then we've got this mirror here. And here's the center of its curvature. And here's R, which is 1.00 centimeters. And then out here is our candle. A little flame on the thing. Okay, and that's our object. All right, well, here's some stuff we know already. And we figured this out on the first problem. I didn't draw that very good, but there's our symmetry axis. But when we had the object outside the focal point, and if this is the radius of curvature, remember the radius is twice the focal length. So here's where the focal point is going to be. But when we had an object outside the focal point, we ended up with an inverted image that was on the real side of the mirror. So the image is going to be over here somewhere, and we just have to figure out where it is. Well, we've got that 1 over s plus 1 over s prime equals, actually it's equal to 2 over the radius of curvature, which is 1 over f. So let's just use the radius of curvature this time. And we want to know where s prime happens to be. Well, 1 over s prime is equal to 2 over r minus 1 over s, which is, let's see, 2s over rs minus r over rs. And that looks like 2s minus r over rs, or s prime. Why, hello there, puppy. You're not supposed to be up here. I've got a dog on my lap right now. So let me get rid of her. You're not supposed to be in here, critter. I shouldn't have left the door open. Anyway, RS over 2S minus R.
Sorry, she got over the box.
You've got a stack of boxes at the bottom of the stairs, so she can't come up here, but that doesn't stop her. Anyway, radius of curvature, 1.00 meters times S, which is 3.00 meters, divided by 2S is going to be 6.00 meters minus 1.00 meters. So that looks like a 3 on top and 5 on the bottom. So S prime is going to be 3/5 of a meter with 3 significant figures, or I think that's 0.600 meters. So it's going to be in here. The magnification in this case, minus S prime over S, is going to be minus 0.600 meters divided by 3.00 meters, which is minus 1/5. And so here, let's see, center of curvature, radius of curvature was 1 meter. We're going to be at 0.6 of a meter, and we're going to have a little dinky candle right there. So, but it's only going to be 0.600 meters away from there. So there's another fairly basic problem that we solved on there. Let's see. Let's do one more problem. We haven't done any problems. Oh, we already did that one. We haven't done any problems with a convex surface. And here's one that's pretty weird. When you look at a Christmas tree ornament, that's a convex surface. If it's one of those nice shiny balls, that'll be a convex mirror is what it is. And we have an object 15.1 centimeters from it. So 6.08 centimeters in diameter. So that's going to be this. That makes the radius of curvature of this thing 3.04 centimeters. So, and we've got this thing 15.1 centimeters away, whatever it is. Looks like an arrow to me. So that must be what they're talking about. So anyway, here's our object. (15.1 centimeters away. The radius of curvature here is 3.04 centimeters, but I need to deal with the sign on this thing. So I'm going to go to my sign conventions for mirrors. R and F are negative if the center of curvature is in back of the mirror. The back is the side the light never gets to. So I've got a negative radius of curvature in this case, and also a negative focal length. So this should be a minus 3.404 centimeters. And let's see, you've got S is positive. The object is in front of the mirror. Let's figure out where the image forms. Magnification and position. Well, let's figure out the position first and then the magnification. So 1 over S plus 1 over S prime equals 1 over or 2 over R. I'm just going to go with that. And let's see. So 1 over S, I think I just did this, didn't I? 2 over R minus 1 over S, which is 2S minus R over RS. I think I've done this a time or two today. So, and practice that. See if you can just whip through that thing and get the correct result. S prime is going to be RS over 2S minus R. So R is negative, minus 3.04 centimeters. times S, which is 15.1 centimeters. And on the bottom, I'll have 2 times S, which is, that's S. It'll be 30.2 centimeters minus R is negative, so minus negative 3.04 centimeters. So multiplying that stuff on top, minus a minus is a plus. So on the bottom, I'm going to have 33.2. Well, I can only keep 2 sig figs or 3 sig figs down to the nearest tenths place. So minus or 33.2 centimeters there. And on top, 3.04. 15.1. I get 45.9 minus 45.9, which gives me 1.38 minus 1.38. Okay, so the image, and that's centimeters, this is centimeters squared on top. The image is going to be 1.38 centimeters behind this. So it'll appear to be there. And then minus sign tells me that it's behind it's going to be a virtual image. The magnification is going to be minus S prime over S, which is minus a negative 1.38 centimeters over S, which was 15.1 centimeters. And minus, it'll be upright. Okay, I'll have a positive magnification, but it's not much. It's only about 9.2 times 10 to 0.092 is what the magnification happens to be. So about the 1/10 the size. So if this object over here happens to be your face, it'll appear shrunk on this thing. It's only going to be about 1/10 its size, but it'll be upright. And that's something that you can look at a Christmas ornament that's a shiny ball and see that. So there's our only convex mirror problem. I think I've got another one somewhere, but for today, that's a good sampling of concave and convex mirror problems. So I think I can stop here, and it looks like I forgot to click on the visualizer to get rid of all that other junk that's there, but that's okay. All right. Well, there are only 2 of you today, huh? Everybody else must be working on something that they have to turn in this afternoon.